hot topic, and just looking here in our lecture hall, I see that you have sparked a lot of interest, Frank. In fact, I don't have to introduce him, but I will, of course, introduce him. Frank Leymann, famous for all his work in workflow systems, infrastructure, middleware, cloud systems. But this is not why you are here. He's also an IBM Distinguished Engineer, since 20 years back in academia. This is also not the reason why you are here. You are here because he's one of the few computer scientists who has studied, in fact, maths and physics, and therefore he knows what he's talking about when he talks about quantum computing and today post-quantum security. Frank is a honorary professor of TU Wien, where we are very fond of to have you here. He's giving regular lectures on quantum computing at TU Wien, and without further ado, Frank, it's your floor.
Thank you very much, Gertie. A fun story is that I'm a mathematician and a physicist, but I'm an astrophysicist. So the opposite, and not the small quantum part. But okay, it helps a little bit. So welcome to the talk on post-quantum security. I asked Gertie, can I consume the 2 hours? She said yes, nearly. So I'm not sure. You can ask questions in between, because the matter is non-trivial, right? Otherwise, I leave 15 minutes at the end. And if you don't interrupt me, right, maybe then I'm faster than 90 minutes. So the talk is structured as follows. I give a short introduction into classical encryption and show what the hell does that have to do with discrete logarithms. Then I give a 10-minute overview on the nitty-gritty details or the important things in quantum computing and what the hell has this to do with discrete logarithms. And then I give a glimpse on the Shor algorithm, which is an algorithm that can solve discrete logarithms. Then I introduce something that is not classical, that is lattice-based cryptography. By the way, I pass the handouts to Gertie, and then you can get the handouts. And what I see is we also take a video that will be published on the website of TU Wien, right? So then I introduce lattice-based cryptography. I give a glimpse on 2 algorithms that are currently standardized called Dilithium and Kyber. These are supposed to be quantum safe algorithms. And then I give a very brief overview of what's happening in the industry, right? And I will only show you what big companies are doing, right? And then I close with a summary. And I hope that you are then nervous enough, if you are from industry, that you urgently run back into your office and start working on post-quantum security, because otherwise your company is bankrupt in 3 years. So, classical encryption, discrete logarithms. This is RSA. I don't discuss the details here. I have a couple of examples, but I don't give it. So RSA says you start with 2 large prime numbers, P and Q. Then you compute their product, N. Then you compute the Euler function of this n, which is p minus 1 times q minus 1. Then you choose your private key. It's a small integer g, such that phi of n and g are co-prime. That means the greatest common divisor between phi of n and g is equals of 1. Then you determine a solution of this equation here. You take d, which is something that you need to compute. D times g is congruent 1 modulo phi of n. This is a logarithmic fast algorithm, Euclidean algorithm. And then this d and the number n is then the public key according to RSA, and g, this number that you've chosen, is your private key, and then you destroy the numbers, of course. Yeah? And then how do you encrypt a message? You have a message, and the assumption is that the message is small, you turn it into a binary representation, right? Then you split it into blocks of size less than n. This is the assumption, so that the message is then a concatenation of the smaller chunks of the message. Then you encrypt the message by using mu to the power of d modulo n. This is the encrypted message. And decryption happened. You take mu bar, take it to the power of g, which is your private key modulo n, and then you get the decrypted message. So that basically means cracking your private key means to solve this equation. And it requires, because d is public, it requires that you need to compute phi of n. And phi of n can be easily computed if you know the prime factors p and q, right? So that means determining the factorization of the number n, and you know that you only need two prime numbers because n is always, according to RSA, product of two prime numbers, right? You need to factorize n, and then you can crack a key. Sounds very easy. So what we have here is, I'm going back, what we have here is, we have this, this module function. And based on this module function, you determine, define a function called the module exponential function. It starts with a natural number n, and then you compute a natural number a, then you compute a to the power of x modulo n. This is the exponential function of x, right? And then this exponential function is a periodic function. Periodic function means you find the minimum number p, so that x of p equals x of 0, which means that a to the power of p, xp is a to the power of p modulo n, equals a to the power of 0 modulo n, which is 1 modulo n. That means that a to the power of p is congruent to 1 modulo n. That means this n is dividing a to the power of p minus 1, which means to find a number k such that k times n is a to the power of p minus 1. So exp has a period of p if and only if a to the power of p equals 1 modulo n. This is elementary math, right? Simple math. So cracking keys again means I need to find the factorization of the number n, right? So that again, we know that a to the power of, so, and I will show you that this means you need to determine the period of the exponential function to the base of a. So we know that a to the power of p equals 1 modulo n. So that means there is a k, so that a to the power of p minus 1 is k times n. Now we make an assumption that a is an even number. If a is an odd number, you made a wrong choice. You choose an even number, right? That means if p is an even number, you can write, according to the binomial formulas, a to the power of p minus 1 is a to the power of p half minus 1 times a to the power of p half plus 1. That is the trick, right? And because this product is k times n, you know that the first factor has a common divisor with n, or the second factor has a common divisor of n, which turns out to mean that the greatest common divisor of to the first factor and n, and the greatest common divisor of the second factor and n is a divisor of n. So if we can determine this number p, such that a to the power of p equals 1 modulo n, you can determine a divisor of n, and you can iteratively apply this. That means you can determine the prime factors of the period of the exponential function, right? So, and this basically means if the exponential function is a to the power x mod n, the smallest number y, such that a to the power of y equals z modulo n, is called the discrete logarithm. The discrete logarithm of z with basis a, right? This is a map, maps an integer and a natural number to a natural number, and as usual, exp of log is the identity and log of x is the identity. Here's an example. 2 to the power of 4 is 16, and 16 divided by 11 leaves the remainder 5, so 16 equals 5 modulo n. That means the logarithm of 5, is 4, the power of 2 here, 2 to the power of 4. And we know that the exponential function has a period p if and only if x to the power of p equals 1 modulo n. That means the period of the exponential function is the logarithm of 1. That means factorization can be reduced to discrete logarithms. You need to compute the discrete logarithm of 1, and then you have the period of the exponential function, and this means you can crack easily keys based on this thing here, based on this fact. Yeah, so discrete logarithm, this is it. Right? Determine discrete logarithm, and quantum computers can easily compute discrete logarithms. Elliptic curves. RSA is not everything. People, we are using in practice elliptic curve. What the hell is an elliptic curve? Wir haben Platz hier vorne. If you want to, yeah, if you want to come into the front row, that's absolutely fine. Okay, you want to sit over there. If it's convenient for you, that's fine. Okay. Elliptic curve. An elliptic curve is a very simple curve. Yeah? Here's the equation. y square equals x cubed plus ax plus b, and the coefficients a and b must satisfy this simple condition. Then you have a curve C. The curve is symmetric to the x-axis, as you can see here. This is the elliptic curve here. And if you have a curve, then the symmetry means if you have a curve, if you have a point P on the on the curve, the mirrored point is also a point on the curve. And this, now you can do the following construction. You can now introduce the sum of 2 points, and I write it now as a product to make the relation to discrete logarithms more clear. So I take 2 points, P and Q. I take the line between P and Q, it intersects the curve, then I mirror the point, and this is then the point P times Q. If I have a point, if I only want to square a single point, I take the tangent at the curve, it intersects here, I mirror it, and I get P square. If the tangent does not intersect the curve, then I introduce a new point, the infinite point, so that in this situation, P square is this infinite point. You can nearly easily show that this is now a group operation. It's a commutative and Abelian group. You can do some computations here. This is an elliptic curve. How does cryptography come into the game? Well, if you have so the parameters A and B of the curves are published. Then you take a fixed point G on the curve, which is called the generator, and you publish this point on the curve. Each participant chooses a natural number S, and then G to the power of S is a point on the curve, which is the public key of U. And the secret key is your S. And cracking a private key means to compute S, which means compute the discrete logarithm of P again. That means cracking elliptic curve cryptography can be also reduced to compute discrete logarithms. And because quantum computers can compute discrete logarithm, elliptic curve cryptography can be cracked. And it can be far more easily cracked than RSA. Right? You can simply find out breaking ECC, elliptic curve cryptography, requires much less qubits than factorization, orders of magnitudes fewer gates. Right? That means cracking ECC with quantum is easier than cracking RSA. And remember that ECC has been introduced because RSA was thought to be not so secure in far future. ECC is much easier to be cracked on quantum computers than factorization. And the elliptic curve encryption, very briefly, you have the generator and the parameters A and B published. Right? Then you compute your public key, S is your private key. Encryption happens, you take a message M, map it to a point on the curve C, and you do it as follows. M is represented as a bit string, which is a natural number, and then you compute Y according to this equation, and then the point M, Y is then the encrypted message. Right? Then you choose a random, nearly the encrypted message. Then you choose a random K, you compute this point, G to the power of K, G is the public generator. This has been randomly chosen, the K. E2 is the point times P to the power of K. Then the encrypted message is this pair, and encryption works as follows, right? The E2 part is multiplied with E1 to the power of minus S. S is your secret key, and then you find out what the message is. Very easy. And again, in practice, ECC is not used for encryption, most often for key exchange and signatures, right? But it can also be used for encryption. And key exchange works, it's a variant of Diffie-Hellman. I will come back what Diffie-Hellman is in 1 hour or so, but it's elliptic curve Diffie-Hellman. You take the generator, and if you want to exchange a key, Alice uses her private key and computes G to the power of SA. Bob uses his private key as Bob, G to the power of S, Bob is PB. You exchange PA and PB, and then you do it very simple. Alice computes the key A, that means what she received from Bob, PA with her secret key SA. Bob does similar, KB is that. Then you simply compute that the keys are the same, so you have established a symmetric key, right? And then you can encrypt the message and so on, right? So this is very easy, but again, this can also be solved. So how does quantum computing help? Very, very brief. Quantum computing, many of you may know this, right? is the basis is a qubit, and the qubit is something, it's a superposition of the two classical states 0 and 1 at the same time. That means a qubit is in the state 0 with probability, so alpha and beta are complex numbers, and the modulus squared is the probability if you measure your qubit to find it in state 0. If you take the modulus of beta squared, it's the probability if you measure the qubit, it's in state 1. So it's a vector of length 1 because modulus alpha square plus modulus beta square equals to 1 because the probabilities must add up to 1 because if you measure, it's either in 0 or in 1. So quantum computing has to do with vectors of length 1. That means it's a point on the unit sphere, but note it is not as simple because alpha and beta are complex numbers. In fact, this is a beast in c to the power to c2, which is R4. That means this is the three-dimensional sphere that I'm drawing here. Very hard to comprehend, but luckily there are polar coordinates, and this gives rise to something called the Bloch sphere. The Bloch sphere takes a point on a two-dimensional sphere. You have the angles theta and rho, and here's how you can represent a point on the Bloch sphere, which is a quantum state. And quantum physicists, they live and die. They can imagine how to manipulate the qubit. I can't do that. So I can't invent a quantum algorithm. I need a quantum physicist for it, but these quantum physicists, they immediately understand how to rotate a qubit on a sphere in order to result in certain effects that I don't really get. So intuition of a qubit is this is a bit. A bit is either 0 or 1, and the qubit has an infinite number of potential values. Any point on the Bloch sphere is a possible value of the qubit. So you have, in fact, uncountably infinite possible values, much more powerful, so to speak. And then, like a classical register, you can combine qubits into a quantum register. And if you have n qubits in a quantum register, right, you have 2 to the power of n potential states in the register. Namely, this is 0, so this is the superposition of these 2 to the power of n different states. And quantum parallelism means while a classical register with n bits always has a single value, a quantum register with n qubits has 2 to the power of n values at the same time. That means a quantum computer, if you apply an operation on a quantum register, it manipulates 2 to the power of n values in a single step at the very same time. This sounds not very surprising, but if you take 50, right, 2 to the power of 50 is in the order of petabytes, so to speak. Yeah? 10 to the power of 15 values are manipulated at the same time in a single step. If you have a register with 300 qubits, 2 to the power of 300 is about 10 to the power of 9t. That means, this is the number of atoms in the universe is less than 10 to the power of 19. That means with 300 qubits, and IBM has 433 qubits online, and you work on them, right? You would need to turn each atom of the universe into a bit in order to simulate what a quantum computer with 300 qubits can do. And if you remember that for free, IBM has machines with 127 qubits online available, you can fiddle around with a quantum computer already. Dramatically, effects can be solved. So, and next is entanglement. A quantum computer doesn't have only the capability to manipulate a huge amount of data in a single step, but these bits can also be correlated. So if you manipulate a single qubit in a quantum register, you manipulate a single qubit. But if you entangle them, you introduce them in a special state that they are somehow coupled, right? If you now fiddle around with one qubit, all the other qubits are manipulated too, yeah, in a somehow coherent manner. Right? This is entanglement. This is a phenomenon that you cannot reproduce in classical computing. It's a sheer raw quantum computing mechanism. And there is a famous intuition behind it. You have 2 qubits, these 2 dices that are somehow entangled. Then you bring them in arbitrary distance, right? So I keep my black dice here, you fly to the moon. If I roll my dice now, right, and then I see the result 1, immediately I know that your dice also shows 1. Right? This is absolutely fascinating, and people don't understand why this happened. And a few years ago, people understand it has to do with black holes and wormholes in space, because the most believed theory these days is that there is a wormhole between the two qubits. If you dissect them and bring them to different places, far apart in space, the wormhole is still there. It's very small, and if you manipulate one qubit through the wormhole, they communicate and immediately show the results on the second qubit. Right? Very strange things happen here. As I said before, entanglement is unique for quantum computing. That means any computation on a quantum computer that does not involve entangled qubits can be realized in principle on a classical computer. In principle means, remember, n qubits require 2 to the power of n classical storage, right? And so the highest computers we currently have can simulate computations on 46 qubits. Right? In Jülich, for example, there's a supercomputer consisting out of 5,000 GPUs, and they, if I remember correctly, can only simulate 46 qubits. And we have 433 qubits. You can't simulate it classically. So in principle, you could do that if you turn each and every atom in the universe into a bit. Then you could have this world computer and manipulate 300 qubits. But there is a very famous theorem by Shor and Leymann that says every quantum algorithm that shows exponential speed up, and we know a bunch of them, compared to classical algorithm, must exploit entanglement. So entanglement is fundamental for the power of quantum computers. And in fact, if you take a look at an algorithm, you bring your quantum register in superposition, you entangle the quantum computer, and then you start your proper algorithm. Right? So entanglement on most of the algorithm happens immediately. So this is now the Shor algorithm. The Shor algorithm starts, you have your register here. I split it in two parts, A and B. I initialize it with 0. This is the ground state of a quantum computer. Then you apply something that you don't need to understand, the Hadamard transformation on the first part of the quantum computer. Then you get the superposition of all the 2 to the power of n states of the first pass of the quantum register. Then you compute the modular exponential functions in your quantum computer. A subfunction is called an oracle function. It has nothing to do with the company Oracle. It has to do that somehow you ask for the values, you query the values on the quantum computer because nobody understands what entanglement is. Like an oracle says, this is the value. Then you apply something, that is called the quantum Fourier transformation because you want to determine the period. What do we do in classical computation? We use Fourier analysis in order to find out what periods are, right? So we apply that to a quantum computer. There's a very famous quantum Fourier transformation. I do that, and then I measure my quantum computer. And what I get out of the quantum, so what I use here is, first of all, I use superposition, as I explained before. The oracle function, this operation here, creates entanglement between the qubits, and it uses quantum parallelism in order to compute a value table of all values of the x part of the quantum computer and the value of the modular exponential function. In a single step, I compute for the 2 to the power of n values the value table. I have for each superposition state its corresponding value. In a single step, I get a huge value table. And then I measure what I got here. And then I apply, some of you know that continued fraction analysis. I analyze the result with classical arithmetic. And if you want to understand that, Johanna and I have written a paper how to, on continued fraction, how the Shor algorithm basically works.
Why do you only measure the A register?
Very, very subtle. You can measure both, but measuring the A register satisfies. And because measurement takes time, you try to measure as few qubits as possible. And it is suffice to measure only the A part. Yeah? This paper, 60 pages, shows how it works. Yeah? But we have Friday evening. So, this determines here the period. Here's a comparison. This is a logarithmic, this is an exponential speedup. A classical algorithm has this growth here, the best known classical algorithm. Shor's algorithm has a logarithmic growth. And if you have an error-corrected QPU, QPUs today are very sensitive to actions of, for example, if a meson from outer space hits a qubit, it collapses. So today's quantum computers are error-prone. right? The state of a quantum computer is kept for a couple of milliseconds. It's depending on the technology. You can hold it for a couple of seconds on ion trap computers. And the number of operations you perform in parallel, each operation has a little error because an operation is always a rotation on the Bloch sphere. And the rotation, if you have an irrational number except pi, right? If you want to rotate on a sphere, then you always have a little tiny error, and it piles up, right? And this error correction is something most people are currently working on in industry and academia to make quantum computers error prone. If you have error corrected, if you're an error corrected QPU, then so RSA 2048 has been defined in such a manner that you need the lifetime of the universe in order to crack an RSA 2048 key, right? So based on the best known algorithm. Based on a quantum computer with a couple of thousand qubits, it can be cracked in, if you have a 1 gigahertz quantum computer, and in 2019 IBM's machines run at 5 gigahertz, as far as I recall correctly, right? You can crack it in about a minute, right?
That's a question. So, but that's the frequency, the cycle frequency of the error-corrected qubit, of the not the physical qubit, but the logical qubit.
Absolutely correct.
And the logical qubit usually requires 2 to the 30 operations
No,
or something.
I
like that.
come back to the in the very. This is all logic qubit, not physical qubit.
You need many thousands
Yes,
of logic.
absolutely, to apply error correction. Absolutely correct. So require qubits and fidelity,
Yeah.
right? So if you want to factor a number z that has n bits in binary representation, right? In order to run the Shor algorithm, you need 5n plus 1 logical qubits, and you need 4 times n to the power 3 operations. We call it gates. And this has been defined to be a CRQC, a cryptographically relevant quantum computer, right? If you have this one, then you can crack Shor's algorithm. For example, RSA 2048 means you need 10,000 logical qubits and about 1 billion of operations, right? And today we have about 400 qubits. You can run about 1,000 of operations, right? It seems to be far away.
The Rydbergs have 10,000.
Pardon?
The Rydbergs have 10,000.
Yeah. This is why I have this approximate, yeah? Okay.
This 10 to the third is 1,000 operations. Is this like 1,000 operations per second, or is this 1,000 operations until the error accumulates?
Say that again? Yeah. You can simply compute. It's a linear error propagation, so it's
So like,
not.
like if the algorithm would take more than 1,000 steps, it would not be.
Absolutely. Then you run out of the error interval. Then you get a noise. You get basically noise. Seems to be out far away, and we can rest. Oh, sorry. Good. Great.
And I guess that we cannot interrupt the operation
No.
after 1,000 steps and remove the errors in some way.
Very smart question. This is how it begins to work. There are some error correction operators that use some sort of approximation. Your errors are piling up, then you measure, and then you compute back, right? There is a line between the uncorrected, the corrected, the uncorrected value, then you compute back. So this is what IBM and others are currently doing in their machines, right? But this is not production ready yet, right? But what I'm discussing here, it is so fast evolving, this quantum computing thing. What I say today can be wrong tomorrow because a lot is happening. Industry is investing a lot of money. Researchers are working here. So it seems to be far away. For a few seconds, I would like to cool you down.
Just a question on the 5n plus 1. Why is it a linear function? Why is it not quadratic?
Say it again?
Why is the number of qubits not quadratic in n?
I don't know. We need to take a look at the paper. Is there the quote on the 2 slides 4 is a paper reference how they perform the computation. Yeah?
Because in the original Shor you have to make quadratic.
Yes.
Really.
Yes. Yeah, but the paper shows you can modify the algorithm so that you need linear growth.
Is it modified?
Yes, a little bit modified algorithm. But there's an advancement in error correction. Error correction, what IBM has done early this year, right? they have shown that they implemented 12 logical qubits with 238 physical qubits. That means they need 24 physical qubits in the average to realize a logical qubit. So a few months ago, I would have said that you need at least 1,000 physical qubits to have a logical qubit. It is dramatically shrinking. Yeah, dramatically shrinking.
You know, there was a paper a week ago that has 48 physical, 48 logical qubits.
Yeah. Okay. Good.
In Rydberg.
Yes. Okay. Okay. Yes. It's not production. Hey, Rydberg, right? Yeah. That means 10,000 logical qubits will require 240,000 physical qubits. If you take a look at IBM's roadmap, they have it end of this decade, right? This number of physical qubits.
Doesn't it also depend how much of a distance code you need to do?
Say it again.
How big your error correction distance code is? Because I mean, all these the first examples were ion traps to show a physical qubit and things like that. But for them, there was just the size of the qubit.
Absolutely
the
correct.
Qubit was not the error correction was not valid for a really large computation.
Yeah.
You usually need an area.
Absolutely correct. It depends.
24 things around this.
Yes,
So
absolutely
the number
correct.
of qubits is still much larger, I think, for really large.
It depends. It really depends on the algorithm that you are running, right? So this is the decoherence, so to speak, is modified here. You still need to apply the error correction code that you want, or other techniques. They are using machine learning within the machine, outside of the machine. A lot of work is going on how to error correct it. So I would keep it really open how much qubits you basically need. But this is the order of magnitude that you need. So next thing, and this is expected in a few years, blah, 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 blah. And then there's an absolutely shocking advancement. A group in China, they have, end of 22, it was really December 23rd, 22, they have factored a 48-bit number with 10 qubits on a superconducting quantum processor, and they estimate that they need close to 400 physical qubits to crack RSA-24, and what they are using is, they are using a NISQ machine, today's machine. And that means they use a variant of the very famous Kyber algorithm. It's an algorithm that has been invented to do optimization, right? They use a Kyber algorithm. Here are the number of qubits, and the circuits they use is, you arrange a circuit in vertical lines, and the vertical lines are gates that can apply it in a single step, in parallel, and then the number of these slices you need is the depth, the number of layers. And they estimate the number of layers to be 1,500 layers and 372 qubits to crack it, while the number of qubits is there. This is still a problem. So the number of layers that you can operate sequentially is much too high, right? So we are still a little bit safe, right? But you can use today's machine already. You don't need error-corrected machines to crack keys, right? And so we are getting close. And what about symmetric encryption? I was discussing asymmetric encryption, RSA. Symmetric encryption is as terrible as asymmetric, because here again a Chinese group. You see, Chinese are very eager. They are working a lot on quantum computing, right? They spend 10 billion, right, on their quantum program. We EU have, I guess, 10 billion. Germany has 3 billion, so Germany is the second highest, and so US is only spending 1 billion because the industry in US is spending a lot of money there. So they use a variational algorithm, an algorithm that can run on today's machine. They call it variational quantum attack algorithm to crack symmetric keys. They showed it on an AES-like symmetric cryptography algorithm. This invalidates two assumptions that have been made by them. Symmetric encryption is quantum safe, and error-corrected QPUs are needed to break encryption. And this work basically shows no, the assumptions are invalid, right? A symmetric key is not quantum safe, and you can use today's machines in order to crack symmetric keys. I hope that you are nervous by now. So now we turn back to lattice-based cryptography. We turn to lattice-based cryptography because this seems to be a rescue. what about the basics about a Gitter? Auf Deutsch, a lattice is Gitter. Yeah? What is a lattice? You take independent vectors, and then you take all integer linear combinations, and then you result in points. So if I take vector v1 and v2, right, these are here 2 points, and I take integer multiples, and I add them up, I get these green spots in the plane. Right? So most often I will assume that the number of vectors is the number of the vector space, right? So lambda is an abelian subgroup, right? You can add them, you can jump from one dot to another dot. Very simple. An equivalent definition that we need in some 20 minutes is a lattice is a discrete additive subgroup of the vector space Rn. That means lambda is a set that is closed under addition. And discrete means there's an epsilon, so that 2 points in the lattice are at least epsilon apart. Discrete, right? Here is how you can prove it. But what it basically means is, if you take a matrix, right, and you take integer vectors, then the integer vectors that solve m times x equals 0 is a lattice, right? How can you somehow see that? From a high level, obviously z to the power of n is a lattice, right? Integer vectors can be added and subtracted and so on. It's a group. It's obviously also discrete. Yeah, discrete, because the points are, you can have balls around them, you can separate them. If you take a regular matrix, then m times x is again a lattice. The additivity is clear, discreteness is not trivial to show. Then m times x, you can take the columns of the matrix M, multiply them by the integers, so m times x is in fact a linear combination of the column vectors mi. So this is a lattice as I defined before, and based on this you can see that the solutions of m times x equals 0 is a lattice again. And this is what we will use when we define lattice-based cryptography. A lattice, so if I define a lattice based on these very nice vectors b1 and b2, I can do some very nice and easy operations. But if I use the basis c1 and c2, they are somehow ill-behaved. One vector is short, the other is very long. There's a very small angle between the computations with this basis is terrible in practice. Terrible computations. This is ill-conditioned. Well, the question is, do we find a nice base? So if I publish only the red vectors and tell you to perform computations, you will be in trouble. But if you are clever, you say, okay, Frank gave me the red vectors. I would like to compute something that is nearly orthogonal in order to do nice computations. Can I found such a good basis? So the measurement, what a good basis is called the nearly orthogonal basis. So if I have a lattice, then I take the basis of the lattice as columns of a matrix. Then I compute the determinant of this matrix. And you know the determinant from linear algebra is the volume of the parallel top spanned by the vectors. Right? What I then do is I compute the product of the length of my basis vectors and divide it by the determinant. And this is called the orthogonality defect of the basis B. And B is orthogonal. If B is orthogonal, then the determinant is the volume of the parallel top. If they are orthogonal, it's a cubic, right? Then it's I only multiply the length of the vectors. Then you see here it's 1. There is a theorem called Hadamard's inequality. The determinant is always small. The volume of the parallel top is always smaller than the cubic. So they know this beast is always greater or equal to 1. This is the defect. This is a measurement of how good a basis is or how bad a basis is if I want to do cryptography. And the lattice reduction problem said determine the basis B for a lattice with a minimal defect, because if the defect is 1, then I can make very nice and good computations. And this problem is NP-hard. It's okay. If I only publish the bad vectors, you have a hard time to compute good vectors to make your computations in lattice-based cryptography easy. For us computer scientists, this is easy. You have here polynomial algorithms. You have here NP, NP-hard, and here the intersection is NP-complete. Right? So NP-hard is determining a nice basis for a lattice. The first interesting problem for cryptography is shortest vector problem. Shortest vector problem means I have a lattice here, and this is a norm. I would like to find out what is a lattice, a point in the lattice that is the smallest, has the smallest vector, right? X star. And this is a characteristic number of a lattice, lambda 1. Lambda 1 of the lattice is the length of the shortest vector, the vector that is as close as possible to the origin. And if you take Euclidean norm, then the shortest vector problem is NP hard. And for the maximum norm, it's NP complete. So it's strange. It depends on the norms. I don't know why. I didn't take a look at it, but the norm seems to be important here. The next hard problem is to find a basis. The longest vector is as short as possible, minimal. So if I have a lattice here, then, and this B is the set of all bases, right? Then M of the lattice is the minimum over all bases of the maximum of the length of a basis vector. So an M lambda is the minimal length of the longest vector in any basis, and the shortest independent vectors problem. Why they don't call it shortest basis problem, I don't know. The shortest independent vector problem, SIVP, is find a basis. The maximum length is the minimum length over all bases. And this is also an NP complete problem.
Do these base vectors have integral coordinates?
Again,
Do the base vectors have integral coordinates or real coordinates?
they have integer coordinates. The closest vector problem is you have a lattice, you have any point in Rn, any point, you want to find the point in the lattice that is the closest to the arbitrarily chosen point W. Right? This is the closest vector problem. And this is also NP complete. So there's a lot of hard, difficult problem in lattices. So quick summary: shortest independent vector problem, shortest vector problem, closest vector problem are NP complete. Lattice reduction is NP hard, and factorization is in a quantum complexity class BQP, right? Bounded probability of error quantum algorithm, right? Okay, and it is important to understand the following thing. I'm not a security and a complexity guy, so I didn't know that. The difference between average hard and worst case hard. Average hard means take an arbitrary problem and it is hard. Worst case hard means I describe a problem, I take an instance of the problem, and I find a very hard to solve problem. Right? In security, what we would like to have is average case hard. If I choose a key, an arbitrary key, it should be damned hard to crack it. Right? So and short integer solutions is a lattice-based problem. They are average case hard. So they seem to be an excellent candidate to build cryptography on. So worst case versus average case hardness means, there is a problem instance, the worst case, on which each efficient algorithm that we know fails. An average case hardness means I choose a random problem, right? And it is as hard as to solve the worst case instance, average case. And average case hardness implies worst case, trivial, and cryptography should have average case hardness. Worst case hardness does not suffice. Encryption must be hard on a random instance, not only on the worst case or on a worst case instance. And for factoring, that means for discrete logarithm, for elliptic curves and so on, it's as of now not known whether factorization is in P or in NP, P equals NP, and it's even not known whether it's average case hard or it's worst case hard. So why is that a problem? So if you take an arbitrary number and you choose an even number, then it's easy to solve, to find a factor. You divide it by 2. Right? So, but if you ignore the even numbers and only concentrate on odd numbers, it's not known whether it's worst case hard or average case hard. Right? So, but there's a very famous, and I took a look at the proof. It's only nearly 50 pages long. Right? This paper here, it proves that if you use lattice-based problem, it's possible to construct average case hard problems, which are okay. In order, so and then you can reduce lattice-based problems to average case problems. And this kind of problem is called the short integer solution. What the hell is this? You take three numbers NMQ and positive real number beta. You take an integer matrix over ZQ. ZQ is something very strange. It's the set of all numbers modulo Q. You can prove that this is not only a group, it's a field. You can add and multiply it, right? You take this kind of a matrix here, and you call something a beta short integer solution. You need to determine an integer vector over this set ZQ, such that A times Z is equal to 0, but the solution must be small, less than its length must be less than beta. And you can show if you choose beta bigger than this number here, then this problem always has a solution. And there is a reduction, a polynomial reduction algorithm from the shortest independent vector problem, the lattice-based problem, to a short integer solution problem. That means a randomly selected shortest integer vector problem is as hard as the worst shortest integer solution problem. You don't need to keep everything in mind, right? You will see the handouts. If you really like it, you get the handout and then you browse through it again. It's a prime. Yes. Now we come to two algorithms called Dilithium and Kyber, which is hopefully the rescue of the world, right? So we make it even more complicated now. We dealt with vector spaces, and we get rid of vector spaces. We choose modules. Modules are close to vector spaces, but they have very bad behavior. They don't have a basis, right? Computation is cumbersome. Right? And we don't take fields. So vector space is something over a field. We take rings, and the ring does not survive. A ring is nearly a field, but not really. And now we take a ring that doesn't have numbers, but polynomials. Right? Extremely terrible. Right? So first of all, we take a commutative ring, and then we define the polynomial ring over R as follows. We take a polynomial in a variable x over the ring that is this kind of an expression. You know that. You can add to polynomials. You can multiply to polynomials, right? You learned that probably in school or first semester in math. And you can define it equivalently. You don't need to write it as a polynomial, but a polynomial can be understood as a family, a map of the natural number into this ring, such that only a finite number of coefficients of the polynomial are really different from 0, right? Then you define it similar like vector addition, and multiplication of the polynomials are defined as this thing here. And if you define x as a vector that has in the second column 1, you can write each polynomial as this kind of a vector. So there are, and then you can, then there are a bunch of algorithms how to multiply and add polynomials in a convenient manner. So polynomial rings. We need these polynomials. And what we are now doing is there is an algorithm called Dilithium. And Dilithium makes it really weird. So they substitute the field over K vector space by a ring R in order to result in a module that is computational much more inconvenient than a vector space. ZQ is the ring of integers modulo Q. Q is a prime number. Then you take the polynomials over ZQ, and then you take the residue class over xn plus 1, and we are now in abstract algebra. I lost 90% of you if you are not a mathematician. It's absolutely complicated, and it's by will complicated, right? And Dilithium is using n equals 255 and the prime of this number here. And if you take a look at the algebra of these things, these numbers have been chosen by care. Right? They are security specialists and algebraic people, algebraic mathematicians that have shown which kind of prime numbers and which kind of dimensions are especially computational intractable. Right? And these numbers have been chosen by will. Then you have a set BH, which is also a set of polynomials, but polynomials that have exactly h coefficients that are plus 1 or minus 1. The cardinality of this set is this one. And Dilithium is using h equals 60, resulting in 2 to the power of 256 this kind of polynomials. They define a hash function associating a bit vector into this set of polynomials. Then they use matrices, the elements of which are polynomials. And this is then also a module over this strange ring here. And then they use matrices of these polynomials and the vector of polynomials. They choose it randomly. And then they define this shortest integer solution problem in this module as follows. You have a message M that you want to sign. Then the job is to find a vector Y, but Y is a vector of polynomials that is smaller than beta. Of course, we need to define what the norm of a polynomial is, such that the hash of the following vector, you take the message, is considered as a vector, concatenated with a solution of a matrix. The first part consists out of this randomly chosen A. T is also randomly chosen, which turns out to be your private key. This is the identity matrix times Y. This Y must be computed. And Y has this form. It consists out of R1, C, and R2, and this becomes then the public key. The situation is as follows. You have a lattice, but the lattice is not a set of points. It's a set of polynomials. It's a set of tuples of polynomials. And the quote-unquote dimension, there is no dimension of a module. You only have something like called the degree. So the dimension, quote-unquote, is 256, high-dimensional space. And then all computation are done modulo Q, which is also complicated. And Q is this huge prime number. And the second algorithm I'm going to introduce is called Kyber. It's using a smaller prime number. And you need to multiply polynomials, add polynomials, and you use something that's called number theoretic transformation. Then only very few people understand it, hopefully you.
I'm not sure about that. My question would be, how practical is that algorithm for microprocessors?
I can show you how long it takes on a typical QPU, but there are already companies that are building ASICs in order to make it effective. So it's not really effective, right? So if you're an IoT person, you are in deep trouble. Okay, welcome. So dilithium in a nutshell means this is a hash function that the standard defines, psi. This is the matrix you want to sign, the message you want to sign. This T is your secret key that you have chosen. This very strange vector of polynomials is your secret key. The matrix that you have also chosen is your public key. And the signature is this vector that you have to compute. The details is here. There's a very nice, here this first reference is a blog of a lady. Absolutely fantastic. You can read it at any time. Nice to read. She explains dilithium very, very nicely. And this is what I will call in a minute a learning with error problem. Because this expression in the hash function is this kind of a linear equation. And this linear equation has a term that is an error. And you want to solve linear equation up to a certain error. Learning with error. And so dilithium is something that's called a learning with error problem. And the other algorithm, Kyber, is also using learning with error. What does learning with error mean? Learning with error means I have a linear map, and I've given samples x and y, such that f of x is equals y, and linear algebra makes it easy to determine the function f. Right? You use Gaussian elimination, Gauss-Verfahren. Yeah? And assume that the input xy to the learning algorithm has errors. That means f of x is not precisely y, but it has some little error. So instead of solving the equation a times x equals y for each y, there's a random and a secret vector e, the error, very small, it must be small, such that a times x plus e is equal y. And this is what you need to solve. A and y are public, and x and e are kept private. And this is called the learning with error problem, because there is a secret error. You learn something up to a certain error, and you should find a nearly precise solution. This is hard. This is a lattice-based problem, right? Because you solve a linear equation. I've shown before that this is a lattice problem, right? It's believed to be believed is very important. Belief, because nobody has a solution now, but somebody may find a solution in a couple of years. I will show that how fast this may happen in the next couple of slides, right? It's currently intractable. And the shortest vector problem can be reduced from the worst case hard to the average case hard based on learning with errors. I'll come to that. So now this learning with error is a lattice-based problem. Remainder, 40 minutes ago, I said that the integer solution of m times x equals 0 build a lattice. Now I choose a matrix of polynomials, and this is here a vector b of polynomials, and a and b is a public key. And then I choose a vector of polynomials s and a small vector e, and then the learning with error problem, a times s plus e equals b, is equivalent to solving this combined matrix problem. So this is a matrix, this is a vector. All solutions, SE1, build then a lattice, as I've said now a couple of times, right, or here above. So solution is of this LWE problem, build a lattice. And this vector SE1 solves the shortest vector problem, and S is your private key, right? We are now in encryption. Okay, it's a lattice problem. And Kyber, the compute public and private key, as I discussed before. Kyber is using this kind of numbers. Encryption in Kyber is based on learn with error problems. Again, you take this kind of vectors. I don't dive into the details, right? But it's very same. You solve this LWE problem, and then you encrypt the message. You have a message here, an encrypted message. And then you can prove, you can decrypt it again, and so on. This was extremely abstract, right? And this lattice-based stuff is highly complicated. You must understand polynomials, residue classes of polynomial. You never wanted to learn it, right? So what is the industry doing? So the industry, why should you care today? We discussed NISC machines versus high-end machines, error correction. Will this take long? Yes?
So the question regarding the Kyber algorithm. Do you happen to know whether recent Kyber is a subtraction of the Kyber algorithm? I'm asking this because
Wait, which Kyber?
recent Kyber.
No, I don't know that. I never heard it.
The background of the question was last summer I read an article that recent Kyber was ranked by KI.
Yeah.
That's not
So
anything.
I don't know it. And I would not be very much surprised if it has been cracked, right? But as of today, the algorithm Kyber that I sketched has not been cracked because it has been published a few weeks ago, or it has been cracked within the last couple of weeks. Okay. So industry awareness. The first is it takes a long time. So there are hardware specialists who say the hardware specialists. You can offer them a huge spectrum. Some people say the hardware will be ready in a very few years to crack RSA, to compute discrete logarithms. Some people say about 10 years, and some even say about 30 years. Right? 30 years for me, it's okay, then I'm gone. But many of you will still be there, will still have a problem. But again, somehow my belief would be end of the decade, early 30s, you will basically crack it. But again, you find the whole spectrum. It's a matter of belief. Right? Albert Einstein, Zukunftsvoraussage ist schwer, insbesondere, Voraussagen sind schwer, insbesondere wenn die Zukunft angeht. So, why should you care today? So many data that you have today that should be kept secret, like health data, product data of an airplane, right? You must keep data about an airplane for decades, because an airplane flies decades, and if it crashes, right, you must prove that you as a manufacturer are not guilty. There's secret data. You must keep the data for a long time. And this data will be cracked in foreseeable future. So if you must keep your data for 30 years and you store them now, based on today's methods, people can crack it in 10 years. Very bad news, right? And this is, by the way, called harvest now, decrypt later. This is currently happening. People steal encrypted data and basically threaten you and say you can pay now or in 10 years if I crack your stuff. Harvest now, decrypt later. This is done today. Right? So they break into your into your organization, steal all the data, and lean back and say, in 10 years I will be rich, because I will basically ask you for money. So encryption based on quantum technology requires new hardware infrastructure. For example, for symmetric keys, there is a proven uncrackable algorithm, the BB48 algorithm, that you can use to create and exchange symmetric keys. Very easy to be 10 minutes within a lecture, right? It's proven, mathematically proven, you can't crack it. But it requires the exchange of qubits. Qubits, you can't exchange qubits on today's wires or WLAN, right? So you must have fiber lines between your computers to exchanges. It's very important, very expensive, or laser lines, what people are doing.
So you said that symmetric algorithms are cracked, though? Does it
I need to come to you.
Does that symmetric key exchange have an associated algorithm that's also uncrackable? Or would you use that?
This is a symmetric key. So if, yes. So I wanted to, yes. Yeah. But the exchange, you can't, as a man in the middle attack, right? You can't do that. You can detect man in the middle attack, but once you encrypted something with this symmetric key, you can crack it based on this new algorithm, right? And so and a lot is basically happening here, right? Again, we in Europe is building a fiber line of a couple of 100 kilometers to connect two capitals. I don't know which capitals, basically, in order to have secure communication based on BB48. In China, they have more than 1,000 kilometers. They use a satellite, stationary satellite, send a laser beam to the satellite, reflect it back, and they connect two main cities in China to have secure communication. US is doing something, but it's extremely expensive. Right? You need to carve out each and everything and substitute it by fiber channels or by laser beams in order to ensure secure communication. So if in a few years online banking will be gone, online shopping will be gone, because you can crack everything. We will all go back again to banks, stand in long lines in order to grab money, right? Digital money will be gone, because you can everything crack it, right? If you invest in Bitcoin, good luck, right? It can be cracked. Yeah? The world will be completely different. I see people here, they say, Frank is crazy. Believe me, this is true. This technology is currently going on. So quantum safe procedure require changes in all of software in infrastructure. You need to use the new encryption algorithm. You need to change code. Some of you are old enough to understand the year 2000 problem. This was peanuts against what we need to do with our software to make it quantum safe. Right? So the building infrastructure, it takes many years. So that basically means people are working on post-quantum cryptography, PQC. Some people call it also quantum safe, quantum proof, or quantum resistant. This refers to algorithms which, according to today's knowledge, are secure against attacks with a quantum computer. Important is based on today's knowledge, right? So quantum algorithms, that means the PQC algorithms, are not known to be cracked as of today, but most of the common algorithms are not quantum safe. Everything is based on discrete logarithm, RSA, ECC, and so on. And the corresponding procedures are the hash-based cryptography, lattice-based cryptography. This is why I give you a glimpse on two lattice-based algorithms, Dilithium and Kyber. But again, there is no guarantee that these methods cannot be cracked at some point in time by a quantum computer or even a classical computer. This is a bet. Right? This is a bet. There is no proof, there's no algorithm known that has a mathematical rigor proof that it can't be cracked. But the US guys are, for example, also nervous. Here's a law from this year, the Quantum Computing Cybersecurity Preparedness Act, that has been signed in, I think it's, where do I see it? Nearly a year ago, 22, right? Where it's basically said it's a law, and by law each government agency in the US must start work. They have a timetable. If you follow this link when you have the handout, here, there's a timetable where which agency must report that they followed this law and prepared themselves in one period is 6 weeks, the other is 7 months, and so on and so on. And in 2 weeks, they must all report that they did everything to be quantum safe. So yes, it's taking it extremely serious. What did I do? I followed it. Here's the link. Gehe ich den wieder zurück. Sekunde. Here we go. Then the NSA also recommends to all vendors that have to you don't need to read. All vendors need to prepare. All companies need to prepare, right? Very soon in order to become quantum ready, right? Spend time and resources now to understand the whole stuff. And then there is, in October this year, there comes out a report, worldwide participants, how concerned they are. So companies are concerned about. They are very concerned or not concerned at all because they don't know what quantum is, right? But 50% they are concerned. But being concerned and doing something is different. There are people, we are concerned, we have to do something, right? But then how much time do you have? There's another report from last year. There's a very simple inequality, the Mosca inequality. The collapse time is the number of years until you have until you have cryptographically relevant quantum computers available. 10 years, 30 years, this is a matter of belief. Ask your friendly physicist when he or she believes that the quantum computer is stable enough. My guess is less than 10 years. Then you have the migration time, the number of years you have in order to realize in your company, or we as a society in our environment, a quantum safe infrastructure. And the shelf time is the number of years you, company, you, government organization, must ensure that the data is kept secure. And then if T shelf plus T migration is greater than T collapse here, then you are in deep trouble. Harvest now, decrypt later, right? This is, and the time you have is, the maximum time you have as a company, we as an organization, in order to be quantum safe is the collapse time minus the shelf time. So if you have documents, if you believe in 10 years, as I do, that quantum computers will be relevant for cryptography, and I must keep data 10 years confident, and most often you must keep the data much longer confident, you must start today. Leave the room, rush to your desk, and start working on quantum cryptography. Now secure communication. TLS, I rush over TLS, means works in 2 phases, right? It's a protocol to secure data transport because based on an established key, online banking, for example, right? If you buy something, right, then it's TLS behind it. Right, it has 2 phases. The TLS handshake basically uses an algorithm to establish a secure key. Then you send the message. It's called TLS record phase. Why the hell it's called record phase, I don't know. This is then where you use the symmetric key in order to exchange the message. Right, then Diffie-Hellman, I briefly explained the lattice-based, the elliptic curve Diffie-Hellman. Here's another one that only works with simple arithmetic. It's a very famous algorithm used in practice to exchange symmetric keys. And HTTPS that we are using if we are doing secure surfing, right? It's HTTP on top of TLS. By default, they have a very simple algorithm to establish symmetric keys that is called encrypted secret random number mechanism. And most often this is substituted by Diffie-Hellman, and in future you can substitute it by Kyber, the algorithm that can be used in order to encrypt data based on the Kyber algorithm. And how do you become quantum safe? So let C be a classical algorithm that we use today, and Q be a corresponding post-quantum algorithm like Dilithium or Kyber. So the first method is carve out C of your code and substitute it by quantum safe. Right? That means you install, instead of calling the APIs for implement the classical algorithm, you use an API that implements Q. Yeah, instead of Diffie-Hellman, you use Kyber, for example. The algorithm that is more wise, so the method is you use C plus Q. I call it C plus Q. That means you use both C and Q in parallel. That means you sign a document classically and in parallel with the quantum algorithm. Right? So if the classical is basically broken, right, then you can rely on the quantum algorithm, and it gives us time to gain trust in the quantum, post-quantum algorithm, Dilithium or Kyber. Right? You add both signatures, and then after a few years you say, oh, this post-quantum algorithm is very nice, I use it and I get rid of this classical algorithm. Or you use Q followed by C, or C followed by Q. That means you use again the classical and the post-quantum algorithm one after the other. So you sign the document first, classically, and then the combined document, the document, the classical signature, is signed again with a post-quantum algorithm. Right? Here is an example. You have a message, you sign it with elliptic curve digital signature algorithm, ECDSA, and in addition with the post-quantum algorithm Dilithium. Right? This is the combined approach. But this is not simple, right? Most post-quantum algorithms have excessive large signature sizes. Much larger IoT problem, yeah? It involves excessive IoT problem. It requires very large public and private keys. It requires operations that are asymmetric between sending and receiving parties. It requires the responder to generate a message based on the initial public value, and so on. A lot of problems. Secure implementation may address issues like you must at the sudden validate public keys, you must reuse public, and so on. Lots of problems. This kind of problems, thus it's not simple, drop in a new algorithm and then you are done, right? And the issues that you run in are documented in a bunch of documents, right? I have here 3 documents. This is by NIST, National Institute of Standards. They have a very nice document getting ready for post-quantum cryptography. Here's another NIST document, quantum readiness. Here's another NIST document, tons of documents that explain you, that recommend how to proceed and explain the problems you will run in.
I have a question. I'm not sure if you actually have the answer, but because it's a moral and the political side, I would say. I mean, although the document you are showing us is about the USA efforts,
yes.
And why there is no European effort?
I will show a few European efforts.
Okay.
Absolutely. And I wish that there would be much more European documents. Yeah? Okay. Yeah? So, standardization. So you will run into problems, and there are documents that show you what kind of problems you are running in and how to prepare to solve the problem. And this post-quantum cryptography is currently standardized by the National Institute of Standards, not an EU institution, right? Here's a website, you can go in there. They document the process to submit, evaluate, recommend, and standardize quantum-safe algorithms. An effort that started 7 years ago, 2016. And they standardize 4 algorithms. The first one is called Kyber, that I briefly mentioned. It's called Crystals Kyber. Crystals means cryptographic suite for algebraic lattices. It's Kyber. They standardize Dilithium. So Kyber is for public key encryption and key establishment. Dilithium, Falcon, and Sphinx Plus is for digital signatures. And then they also said, this is the first wave. This has been out. And they are currently evaluating, they announced that they're evaluating Bike and a bunch of other algorithms. And if I'm correct, 1 hour later, once that was on the website, a group published an algorithm that cracks this algorithm, right? So it must be they waited to be published and then they pushed the button and published the algorithm to crack it. This is why I'm always saying this is a bet on the future. We are betting. These are not mathematically proven security algorithms, but as of now, we don't know a classical attack or a quantum attack against the standardized algorithms. Right? I will come back to that later. So the standards here, Crystals Kyber, here's a link to the documentation. Right? It speaks about modules and rings and polynomial rings, everything I said before. In order to read the standard, you must be not a mathematical illiterate. Right? it's fun to take a look at it and say, boo, this is damn complicated. I trust the guys, right? I do the very same. And here's now a European document, right? ENISA, for example, they describe the standards and potential implementations in this document. Right? It's an EU organization, ENISA. And what are others doing? So, for example, AWS, Amazon, they are working heavily on it. They enabled their products called Key Management Services, Certificate Manager, and Secret Manager for post-quantum security. They offer TLS endpoints, and they support Diffie-Hellman, but also Kyber. They use a C+Q approach. If you use these products, you must configure it, but then you are at the sudden quantum safe if you use their products. They have a quantum safe implementation of secure file transfer, right? Also using the C+Q approach. And what they do is they have an IEEE, an IETF working group where they describe what they did, so that others can basically follow it. Right? They are based on OpenSSH, and they use a library that I'm going to discuss in 7-8 minutes, liboqs. Right? And they use Wolf SSL and use liboqs. They combined it in order to get secure FTP. And what they also did, for example, they have a post-quantum safe TLS with their KMS, Key Management Service API, right, against. And what they did is an IETF document with others. They show how to implement TLS, post-quantum safe. Microsoft has an implementation of a VPN that is quantum safe, post-quantum crypto, based on OpenVPN, and they're already using it in practice. What I learned is that Microsoft has an underwater data center under the sea in front of Scotland. Right? They use it there because cooling is cheap, right? Under a high-end compute center under the sea, and they use their quantum secure OpenVPN protocol in order to communicate with this compute center. Right? They are already quantum safe. They also have a post-quantum crypto TLS implementation based on this OpenSSL implementation, and they have also SSH, Secure Shell, quantum safe. And again, here's an IETF document where they describe what they have done together with others. What am I doing here? Google, what is Google doing? It was a surprise to me. What Google, here's the blog, here's the internal communication. Google protects all of its internal communication from quantum thefts. So the internal communication is quantum safe. They use the C+Q approach. And so they address store now, decrypt later attacks, right? Because they want to keep their data safe, right? They won't want to be affected by harvest now, decrypt later. They say that signature is not to be addressed immediately, because a signature is now, and if it has been signed, I need to sign it then again, right? So signature is not yet addressed. And then in 2016, they used an algorithm that was considered quantum safe, New Hope. It's a New Hope-based implementation within Chrome. They released it in Chrome, but then it turned out that this algorithm is protected by IP, by a patent, Google, and then they had to carve out their implementation. And now in Google 16, in Chrome 116, you can configure your browser to become quantum safe. Very easy. You go to configuration, and then you go to a setting you can click on, and then you are quantum safe. Right? So Google Chrome 116 can be used to run quantum safe. Again, based on a C+Q approach. Cloudflare, another company, they also work a lot so they have an open source implementation called Circle. Here's the link to Circle, where you can play around with post-quantum cryptography. They support Kyber and Dilithium under BSD3 clause. They apply it to TSL and make it quantum ready. Here's a link. It is a very nice reading how they implemented, how they included quantum safe algorithms in there, in here boring SSL, and they implemented it in Go, and they applied it to one of their products called Cloudflare Tunnel, so that you can configure Cloudflare Tunnel to have post-quantum secure implementation. IBM does also something. For example, there's Z-series. Z16 is quantum safe to protect data against future threats of quantum computing. DB2 can sit on top of it so that all the data is quantum safe if you use this kind of high-end machine. Right? They use quantum safe cryptography support for key management and transactions in the IBM cloud. If you want to do that, data exchange can be secured based on quantum safe algorithm. They also have a product called Key Protect. It provides lifecycle management for encryption keys, and again, this is also made quantum safe based on a quantum safe TLS operation. And OpenShift is, of course, also working. It's a company acquired by IBM, is also working on quantum safe cryptography. I myself, I'm also working with a company called WSO2. We are doing a prototype. We are making their products quantum resistant. They have API management capability, identity server, some SaaS, some SaaS products called Choreo. It's a cloud-native platform, right? Quantum safe, identities are safe against quantum attacks, and we are working on a programming language called Ballerina that we are making quantum resistant, so that all communication between components that you build in this programming language are basically quantum safe. And this is based on libOQS that I'm following okay, Wolf SL. This is also interesting. Even standards that are building standards for applications like X9, right? It's a standard in finance. They are also revising their standards in order to show how to make the standards quantum safe. So it's not only, and that what I'm showing here is something, is only a subset of activities that is going on in industry. Open source, this is now important. Most of the stuff that I explained until now is available as open source. But of course, in the GitHub repos that you take a look at, they all have a caveat saying all implementations have the caveat that they're experimental prototypes and they don't guarantee production readiness. It's open source, right? So there's an initiative called Open Quantum Safe. Here's the link, OQS. It's an open source project to support the development and prototype of quantum safe cryptography. There are two lines of work. One is called libOQS. libOQS is an open source C library for post-quantum algorithms, and they show how to use the quantum algorithm in protocols like TLS, SSL, and so on. Everything is in GitHub. A lot of contributors, the big guys that I've shown before, like AWS, IBM, Microsoft, Cloudflare, Intel, Cisco, and so on, they contribute, as well as a bunch of universities. Right? So it's a broad effort that are building this libOQS. libOQS, as I said before, it's based on C, so the links are for the handouts, right? So libOQS is a C library based on MIT license, but the libOQS library uses other third-party libraries with different licenses, and they list which licenses are claimed with the code they use. Right? And they build common APIs for these libraries. Here you find the Swagger files, the open API specification of the APIs. They have test and benchmarking routines that you can use in order to test your prototypical implementation. They have wrapper for C++, Go, Rust, Java, .NET, Python. Right? If you are not a C guy, but a Java guy, for example. The prototype is available on the major platform, Linux, macOS, Windows, on different kind of hardwares. They use different kind of compilers, C-Lang, GCC, Microsoft compiler. The algorithms include Kyber and Dilithium that I have explained before, and they applied it to protocols like TLS, SSH, X509, SMIME, and so on. Another EU document that shows how to build protocols. Protocol is include the quantum safe algorithms in communication protocols. Take a look at this one if you want to use libOQS and if you want to build your own prototype based on this. OQS, as I said before, only as a sample. OpenSSH has been made quantum safe. OpenSSL has been made quantum safe. Here's the code. curl has been made quantum safe. VPM, HTTP, Nginx, Envoy, it's a cloud native, you know, the Mosquito, HAPoxy. This is a lot of products that has been prototypically made quantum ready.
But wouldn't that mean that in 10 years we can still online shop, basically? That we have to
If these algorithms are not cracked.
Yeah, if they are not cracked, but let's assume those guys made the job
Yes.
kind of correct, then it wouldn't change anything despite the computing power, right?
Absolutely. But here are sitting a lot of smart guys.
Yeah,
they do everything to crack it. Believe me. Believe me. Because then they are famous. Right? Yeah. So I wouldn't trust, I wouldn't bet it.
Okay.
Yeah. Dilithium, here are some key sizes. And I have links where you can see the key sizes and so on, right? If you download then the documentation. Key generation is simple. You include here some header files, and there's a library, Dilithium 2. You generate the key, you feed a seed in, then you get a public key into a secret key according to this algorithm. Here you can then basically sign a little document, right? Then you can verify the signature. It's, in theory, very simple, right? You write your C programs. Kyber is the very same. Here are some key sizes based on different kind of protection level that you basically have. Here is, I summarized it here, you generate a key for asymmetric in encryption. You encapsulate your message M, you decapsulate the message based on a public key, a private key. Here are some execution times based on the GCC compiler. The execution times are less based on C length, so it's sensitive to the compiler. What a surprise. This is all published, right? This is all in the GitHubs where you can see what are the key sizes, what is the runtime, what kind of CPU do I need, and then we will find out the microprocessor will have trouble. So some of the algorithms, as of today, the algorithms are safe, but many people are working on it to crack it because they want to become famous, rich and famous. So what can you do? The keyword here is crypto agility. Crypto agility means you need to protect against the failure of an encryption procedure. So don't use a single post-quantum algorithm, but use multiple of them concurrently, in parallel. You don't know. Here's a little document that shows the ways how you can achieve crypto agility. Even there is a first open source implementation. This just begins. This is the first open source implementation, right, called Sandwich. Right, here's a link to Sandwich. They built a protocol. They built a little they built a prototype where you can plug in. It's hard to read. Here it's OpenSSL. Here you see libOQS. They use OpenSSL. Plug in libOQS. They have a backend and an API where you can use their backend to communicate in a quantum safe manner. You can use round robin so that each other request uses a different kind of protocol, a different kind of algorithm, and if one algorithm fails, you just plug it out. Right? This is the only approach, because with tomorrow or in 1 year, one of the algorithm Kyber may fail because somebody cracked it. So quantum agility is that what you need to achieve. Right? And here is the GitHub repo where you can take a look on different platforms and play around with their open source implementation that is quantum agile. Summary, 90 minutes. Okay. Summary basically is today's crypto infrastructure relies on the hardness of discrete logarithm. That's what I showed in the first 40 minutes or so. Then quantum computers will be able to crack the infrastructure midterm. What midterm means is some optimists say 5 years, some pessimists say 30 years. In the middle, the truth, as usual, will be somewhere in the middle, right? So lattice-based cryptography seems to be a rescue, average case hard, worst case hard. Standards for post-quantum security are underway, and except for big players, right? IBM, AWS, Google, and so on, right? Awareness is lacking. No, it's not true. We saw a chart that 50% are concerned, right? But what are they doing? We don't know. Open source prototypes are available for the post-quantum security stuff. Quantum safe infrastructure must be agile. And this is what I bring up to mind. Right? Start as soon as possible. Right? If you have documents that should be kept secret, right? Start migrating as soon as possible if you have documents, information that must be kept secret. So this ends the journey about modules and polynomial rings and some problems. Other further questions? I'm happy to try and answer questions. Yeah? But again, you find a lot of documentations really that IoT people are really concerned, right? That if you have micro devices, then you have a problem. If there are no questions, wonderful. I create the PDF. Should I send it to you, Gertie? I send it to Gertie, and then how does it work? They drop you a mail?
Put it online.
Okay, they put it on. Okay. Okay. So, no question. Thank you very much. Be concerned.